G'day guys. A car is doing a lap around a circular racetrack. It starts from rest and finishes with a speed of 200 kilometers per hour. If the car increases its speed uniformly over time, what is the car's acceleration vector A as it crosses the finish line? So what's going on here? We know that the car starts from here, from rest, and then proceeds to go around this circle like this, getting faster and faster, and then it crosses the finish line, which is also where the start line was, so it's done a full lap, and it finishes with a final velocity of 200 kilometers per hour. And we're asked to find the acceleration vector, so that includes magnitude and direction, as it crosses the finish line. Okay? So to understand what's going on mathematically, let me define a variable real quick. I'm going to define a variable, x, which is the curved distance the car has traveled at any particular instant, x. Okay? And we can tell that when x is equal to 0, so when the car is just starting from the start line, that means your your speed of your car is 0, right? That's because the car starts from rest. We can also say that when x is equal to 2 pi r, where r is the radius of your circular track, that means your your speed was 200 kilometers per hour. Right? That's because once the car does a full lap, which equates to a distance of the circumference of this circle, 2 pi r, then the speed is going to be 200 kilometers per hour. And you can convert the units to know that your speed, as it crosses the finish line, is 55.56 meters per second. Now that we've got that down packed, let me quickly talk about the velocity profile and the acceleration profile of our car as it crosses the finish line. Well, hopefully, unsurprising to you, as the car crosses the finish line, its velocity will be tangential to the path. And because this is the finish line right here, that's actually pointing directly upwards, because that's tangential in this position. Right? That's your velocity vector. Now let's talk about your acceleration vector in a little bit more detail. Let's move that up there. Yep, that'll do. Okay, so your acceleration vector will actually have a component which will be at in the tangential direction, and it will have a component, an, in the normal direction, always pointing towards the middle of the circle, an, right? And the combined acceleration vector, which is the one we're trying to find, is the sum of both of these vectors, a. That's what we're trying to find. We're trying to find this diagonal piece just here, okay? So in order to find this diagonal piece, at some point we'll have to find at. And this is where this piece of information is really important. We're assuming that the car increases its speed uniformly over time. So, whilst the velocity is changing, the acceleration is remaining constant. So we can say that at is actually constant, because this thing increases its speed uniformly. That means at is constant, right? And in fact, we know an equation for at, which will be really useful here. We can say at is actually just dv dt, where v is your speed of your car, right? And we can also use the chain rule here to help simplify this out. We could also write this as dv dx, and don't forget, this is the x I'm using just here, this is the variable I'm referring to, times by dx dt. Now, because x has been defined to be the distance the car is mapped out at any particular instant, its time derivative is actually its speed. So we can also write this as dv dx times by our speed v, right? And that's actually just going to be equal to at, okay? Now, fortunately, we can solve this quite easily, knowing that at is a constant using integration. We can bring the dx over there, and this is what it looks like. Let me write it over here. We can write this as the integral of at dx is equal to the integral of v dv. Now we've got a choice here. We can evaluate the indefinite integral or the definite integral by plugging in these initial conditions. What I'm going to do is I'm just going to solve this with putting integrational constants in and solve for the integrational constants. But you've got a flexible way of solving this is what I want to get at. So the left-hand side is going to turn into at times by x. And then on the right-hand side, you're going to get, well, the integral of v is v squared on 2. And then don't forget that integrational constant. Once again, if we wanted to shortcut this, we could have actually put bounds in our integral, and then that would have gotten rid of c for us automatically. But I'm doing this what I think is the easier way anyway. Okay, so let me try and resave this. There we go. I've just made this a little bit smaller, so I've got some space. Now let's find this integrational constant just here. Well, we can do that by plugging in our initial conditions. We know that when x is equal to 0, v is equal to 0. So you can literally plug that in here. X is equal to 0, v is equal to 0. That means c must also be equal to 0. And that means at, unsurprisingly, is actually just atx is equal to v squared on 2. Let me use the same color. V squared on 2, okay? And you might be thinking, well, okay, now we've got an equation relating x and v and at, but what is at? Well, we've got another condition just here which we can plug in. We know when x is equal to 2 pi r, v is equal to 55.56. So let's plug that in. In fact, let me solve for at. We know at is actually v squared on 2x, right? So let me plug that in for you. I'll do it step by step. It's going to be 55.56 squared divided by 2 times by x, and x, don't forget, was 2 pi r, which in this case is 2 pi times 100, right? Because the radius of this track is 100 meters. Don't forget, I'm keeping everything in meters and seconds just here. And then when you plug that into your calculator, you're going to be left with 2.456 meters per second squared. This is a constant value. Whilst this car is increasing its speed uniformly, its acceleration remains constant at 2.56 meters per second. We're not done yet. We found one component of the acceleration, but we also need to find the other component, an. Don't forget, from circular motion formulas, an is given as v squared on r. V squared on r, where v is your is your speed at the finish line, and r is your radius at the finish line. When you plug in those values, you're left with 55.56 squared divided by 100, which when you plug that into your calculator, I guarantee you're going to get 30.87 meters per second squared. Okay? In fact, let me write that in blue. 30.87 meters per second squared. Okay, let me resize this again. There we go, I've resized it just to make a little bit more space. And now that I've resized this, we can actually write our acceleration vector is equal to an en plus at et, right? Don't forget, en and et are just unit vectors, right? Denoting in the normal direction and tangential direction, respectively, right? And when you plug these values in, that's going to be 30.87 en plus 2.456 et, right? So in fact, based off this diagram, a little bit more accurate depiction, if I were to draw it to scale, would be something like this. This would be et, this tiny little vector. Sorry, this would be at, this tiny little vector in comparison to an, because an is so much larger, right? So that's a little bit more to scale. Consequently, this will adjust too, and it'll look something like that. Hopefully, I'm just building a little bit of intuition for you. Okay, so that's a more to scale depiction of what's going on. So we're actually done here. We've finished our problem. We found our acceleration vector in terms of en and et. But depending on whether your professor specifies that he wants your vector to be written in I and j unit vectors or e and t, you'll have to adjust your answer accordingly. If your professor wants you to submit your answer in terms of I, j, and k notation, you'll have to convert en and et into I and j. So you can tell here that en is actually just minus I in this case, and et is actually just the j unit vector. So if you wanted to, right, and it's always good to practice doing this, you can rewrite this acceleration vector in a different way, which would be minus 30.87 I plus 2.456 j, okay? And I think this is a cleaner way to express your acceleration. Notice I've just converted this from tangential and normal coordinates to Cartesian coordinates. And this is your answer just here. And I won't go into it, but if you did want to find out the magnitude of your acceleration vector, i.e. the length of this thing, you'd have to use Pythagoras and take the square root of each of these elements squared. But that is your answer just there. It's a pretty tough one, and I hope that made sense to you guys. Cheers.